I should have changed this affiliation. But, okay. So I begin by okay. All right. So the talk has kind of two parts. The first part is how one can use preconditioning to construct error estimators. I mean, we are talking about error estimators that are usually used in adaptive finite element methods, and that will be residual error estimators that I'm gonna look at. And the second part of the talks, there are techniques in a posteriori error estimation that can be used without geometry, like only using the topology. Those will be like functional error estimators, and they can be used on graphs. And once you transfer this to graphs, you can in fact try to construct algebraic multigrid methods which are adaptive to your problem, and the right-hand side including. But I'll mention this later as well. Okay, so the first part was how preconditioning will actually help us construct a posteriori error estimator. And I'm going to start by some short introduction in the so-called operator preconditioning. So we have a Hilbert space. It, in general, is infinite dimensional, which has an inner product as well as a norm. And there is an operator A that takes H and maps us to the dual. If you want to think about a particular example, take H to be H01 and H prime to be H negative 1. And A to be the Laplace, negative Laplace. Okay. So now I will only consider linear equations because I think if we are solving things on computer, usually we linearize. Otherwise, we cannot solve, I think. At least I don't know how. And when you linearize, then you consider linear problems. Okay. So what I'm going to assume about this operator A is that it is actually isomorphism. So, I mean, if it is not, if the problem AU equal to F is not well posed, that is a different ballgame. Okay, I don't know. So the story here is that we have a well posed problem that means A is continuous. And also A inverse is continuous and satisfies the Bretzi condition, the IMSUB condition, which is written down below, and it will be repeated later. Okay, so what is a preconditioner? Preconditioner is you look at AU equal to F, you multiply by B on the left, and then you try to solve the problem BAU equal to BF. Obviously, if B is equal to A inverse, then you can find your solution immediately. However, this is not the case. B being equal to A inverse, why didn't we solve the problem to begin with? Okay, so the whole key in preconditioning is constructing B. Okay, so requirements on B, the condition number should be bounded independently of parameters that enter your problem. And I want you to note here that I didn't specify the norm, so this norm can change. And also the action of B on a function or on a vector, if you are in finite dimensions, is easy to compute. Much easier than the action of A inverse. Okay, if we are in finite dimensional space, we can talk about applying Krylov iterative methods to the preconditioned system. In fact, even if you are in infinite dimensional space, you can apply conjugate gradient, but only to preconditioned system, not to the original. If you think about Laplacian, the eigenvalues of Laplacian go to infinity. If you know the conjugate gradient estimate, then you will not have, I mean, you cannot have any convergence or anything like that. But if you precondition, you can apply. Okay. Now, typical example here for constructing a preconditioner is let us consider here the Stokes equation, and the norm on H. The norm on H is the usual one, gradient plus the norm of the pressure, L2 norm of the pressure. And now let's try. So this is our A. That was the Stokes equation. Let's try to construct a preconditioner, and we pick the RIS operator. The RIS operator only uses what we had on the previous page, this here, okay? So during the whole talk, I'm gonna assume that you know how to invert Laplacian or something like elliptic scalar PDE, okay? That we supposedly know how to do. Okay, now, okay, so let's look at the RIS operator. This is the definition of it. B applied to a functional, so it should map us from the dual space back to the original space H. And we look at the norm of BA, and okay, this is you take supremum twice, then you use the definition of B. So that means you can remove the B and take the duality pairing here. And that is less or equal than beta, because beta was the continuity constant. So this is nothing, this is trivial. Well, okay. Next is to do the inverse, which again, you take inf of sup as in inf sup condition, and again, remove B, that's the duality pairing, and this is exactly bigger or equal than gamma. By the assumption that A U equal to F is well posed for any F. Okay, so then the condition number, which was defined earlier, is always bounded by beta over gamma. So what I have just shown is that the RIS operator is always a good precondition. But the RIS operator corresponds to some symmetric and positive definite things, right? So if you have in sup condition and your operator is continuous in a certain Hilbert space norm, you can invert the norm and you have a good precondition. Well, what I mean by inverting the norm is you invert the corresponding RIS operator. I hope this is clear. So this is not, of course, this has been known for some time. Somehow the setup is related to the first two references, although earlier references by Lochin and Watten in 2004 and Hipmeyer 2006. But the relations with mapping between the dual and the are, I think, in the first two papers. Okay. So now let me go to say what are residual error estimators and error estimators. So we are given an F, and A is some PDE operator, and we find an approximate solution UH. Okay. And now we can compute the residual. This is the computable quantity. You cannot compute the error, but you can compute the residual. Okay. And so now so I have listed below two references, and those are, so this is a book by Verfurt and also the book by Riccardo Noceto and Oliver Sievert and Andreas Wieser, who is here from Milano, I think. So if you look at what a residual error estimator is, you just have some local approximation of the error, basically, and that's what you show that it is upper and lower bound. Okay. So now let's move on to see how our operator preconditioning will help us to do that. So so the operator preconditioning was not used in these earlier works. So existence of a preconditioner B automatically gives you a two-sided bound on the error. Okay. Now again, the preconditioner here should act on infinite dimensional space H prime. Okay, and we're gonna go later into to see how does this work, how one makes it computable, because infinite dimensions is not computable. Okay, here is the lemma, which has, I think the proof is shorter than the statement. So you see that we have upper and lower bounds on the error depending on the condition number of BA. All right. So basically, the proof is going on here, and every equality here is using the fact that B is the Riesz operator, okay? And B inverse is its inverse. All right, and that's pretty trivial. Right? I mean, you multiply by B inverse and B and so on, and use trivial inequality. Okay, so I kept the lemma here. So if we have, as I said, if we have a preconditioner B, then we have two-sided bound on the error. If we find a way to compute locally its action, because we only need to know, so the condition number is given by what? It's given by inf condition and by continuity constant. So those are things that depend on your continuous problem. You cannot change this, okay? So what needs to be computed locally, and in order to make this practical, is the H prime norm of the residual, okay? The H prime norm of the residual is just BR, R. So if you know how to compute the action of B locally, you have error estimator. Okay, and it is reliable and robust. The constants, again, are the constants that come from your solvability of the original problem, which, as I said, you are not allowed to change. Okay, so what I'll do next is I'll rewrite the preconditioner, the Schwarz preconditioner on infinite dimensions. And I'll use this Schwarz preconditioner and show how it can be used, how it can be localized, and so on. All right. So the way to think is about two-level Schwarz. I don't know how many of you are familiar with two-level Schwarz. I know at least one person familiar with that, or maybe more. But okay, two-level Schwarz, we're going to take as usually uses fine space, where you solve locally and then you put the solutions together. That's not an optimal algorithm. You need to add a coarse grid. Okay, that means subspace and to correct there too. So here we're going to have our finite element space, DH will be our coarse space, and V will be our where the solution is, you know, the infinite dimension space. Okay, so then, of course, the error equation is A times the error is equal to residual. And I'm going to choose a particular splitting in subdomains that are used in the Schwarz method. And this will be the support of the basis functions. Let's say we discretize with P1. I'm using this simple example. One can make it very complicated, but no P, just P1, and we have a triangulation and one basis function per vertex, which is locally supported. Okay, so then we write this is the Schwarz preconditioner. QH is the adjoint of the natural inclusion, which is just known as L2 projection sometimes. Okay, and so every space splitting gives you a preconditioner, which is written right here. Okay, And this one is in particular a uniform preconditioner. That means B is spectrally equivalent to A inverse. The condition number is uniformly bounded depending on how those things overlap. Okay. And now we, of course, according to what we did, we have a error estimator, which is RBR, as we discussed earlier. So what this gives us is, okay, we have to compute, this is RBR right here. However, for finite element method, by definition, the L2 projection of the residual is equal to 0. Okay, so I don't know if you see, but suddenly everything becomes localized. Okay, so suddenly you only compute n local contributions to the error, which tells you where to refine. If these local contributions are big, you refine there. There is a catch though, right? So I have listed here below some references for the Schwartz that you can find these proofs of why this is uniformly uniform precondition. Okay. So Yuan Li, who I was working with, when we found this, then he went to research the literature, and he found that in 1978, Babushka said that, okay, you can use this as error estimator. Now, I don't know if you know where the catch is here, but AI inverse means you solve on every patch a continuous Laplace, okay? So this basically means that, okay, and in their paper, they said, okay, you take higher degree polynomial or something can do something there. But so you also see here why there are oscillation. You know, one needs to add oscillations to the estimator to get a bound below and things like that, or above. The reason is because this. So this is really if you can compute AI inverse, this is a very good estimator. But AI inverse is compact, which means its eigenvalues go to 0. So that means you can never bound this below. Okay, you cannot bound it below. I'm okay with it. Okay, so let me say how this gives an avenue to do many, and we have done some of those things with Yuan Li. So you look at this nodal auxiliary space preconditioning. I don't know if you know what it is. It is taking the Maxwell equations, let's say, and show that few Laplacians, 4 actually, give you a good preconditioner. Okay. Now you apply the technique that I just showed, and that also tells you that, okay, if you know how to do error estimator for the Laplacian, but I already showed that, then you can do 4 such estimators and you get error estimator for Maxwell equation. So for anything for which you have RIS operator as a good preconditioner, you can do it. Actually, you don't have to use the RIS operator. You can use any other preconditioner that works in infinite dimension. There are many of them. Okay. Now, so I also pitch here some I don't know, this is some claim or my thoughts in regard to all this. So if we have efficient and robust estimator, there is a preconditioner hidden there. So if somebody has a posteriori error estimator and doesn't have a preconditioner, you can dig it out of there and have one. I mean, I don't know how to do that. I think a problem is to do dominated advection diffusion equation with dominated convection, because I was trying to ask around. Now I may have not understood, but I think there is no optimal preconditioner with respect to the convection. Neither there is error estimate. But the reason is right there. I mean, if you knew one, you should know the other. That's all I'm saying. Okay. That's all. This is the first part of my talk. I hope it was understood that if you have a preconditioner, you can go do a posteriori error estimate. All right, so now we move to the second part. So we're going to use a posteriori estimator tricks, let me put it that way, to construct coarse spaces for AMG. All right, and I'll explain in some detail what this is and so on. So we're going to be looking at the so-called graph Laplacians, and if you don't want to think about graphs and things like that, I'll point out to you two things. Every discretization, let's say P1 of Laplace or a Darcy equation, is spectrally equivalent to a graph Laplace. The constants of equivalence depend only on the shape regularity of the mesh. And if you have higher P on the polynomial degree. Okay, that means, I mean, what is written this AUV, if you are on a connected graph, this means that only the constant is in the kernel. Okay, and A times the constant being 0 just means you differentiate. So that kind of assumes you have some derivatives. Okay, that's all. If you fix some of those uj or vj to be 0 at certain places, 0 on the boundary, then you get a SPD problem. Okay. So you have the graph, connected graph, you have edges and vertices, and this is known as the graph Laplacian. And so we are interested in doing a fast solution of AU equal to F, where not necessarily the graph comes from a grid. And I'll show some examples. Okay, so there are some operators that I'll use also later and redefine later. I'm going to define them again. But if you have a graph, you have some sort of gradient, which is because you take, this is the incidence matrix vertex edge, where one of the vertices is 1, the other one is -1. If you want to think, it's like integral over the edge of the gradient of phi dot tau. It's like the Nedelec degree freedom on edge, for those who know, who like finite element more. Okay, then one can write this A of U and V as D, gradient of U, gradient of V, and this D corresponds to, you can think about hydraulic conductivity. You can think about whatever you want if you are in the case of discretization. D equal to identity, this is the so-called standard graph of Laplacian, where you have -1 of the elements. All right, so again, not to take the focus out too much, we are trying to solve AU equal to F, okay? If A is singular, but only the constant is in the kernel, we're gonna assume F is a problem to the constant, so that we have no trouble doing any of that. All right, so I already mentioned some of this earlier, and yeah, we have discretizations of PD, diffusion state distance, which is you take the graph Laplacian, you cross row and a column, and you solve the rest of the matrix, basically finding the Schur complement over n-1. And you want to do this quickly. Okay, so that is something like that. Protein interaction and also modeling social networks. They all involve either finding eigenvalues of the graph Laplacian or solving equations. Okay, I'll go to the application that Anna spoke about this yesterday a little bit. That we do in Oslo, which is like 3D, 1D, which originates from Alfio and De Angelo, I think, in 2006, which is modeling like 3D tissue, and you have 1D vessels network in it. And yeah, so those are complicated problems. The model problem is shown there. T can be traced. But because if you are in 3D, you cannot take a trace on 1D, you can average. Okay, you can put this one inside some cylinder and then do some averaging and try to keep T bounded. Okay, well, that's what it is. But the problems look like that. The Lagrange multiplier is there because you want whatever comes from 3D to be equal to whatever you have in 1D. Okay. And okay, now the Ries operator looks like that because when you try to prove in subcondition, lambda is in some fractional space because you may have some interface, right? And you are taking averages on lower dimensions. I don't want to go into detail into this just because I'm not very well versed in this, and there are experts here that will probably knock me down. So I don't want to do that. I just want to say that we have down there a sum of two Laplacians, and the star means that because we move between dual and primal space, right? So the star is just giving you what you need. You know, it could be Hodge star or whatever gives you back from the dual to the primal. Okay. So here is a typical network is shown in the middle, and I'll show you another one soon. And okay, now we want to approximate what was down here in the 3-3 block of this Ries operator because we want to invert the Ries operator because that will give us uniform preconditioner, right? By what we said at the very beginning. So you only need to know how to invert the Ries operator. Okay, we have Laplacian plus some x. This you can think is identity. And another one-dimensional Laplacian plus some y, which is also identity. And then you have this creature down there that you have to approximate. So we choose to approximate it with rational approximation. I mean, there are probably other choices, but I have to say that if you drop one of the terms, I think all the known techniques amount or can be written as rational approximations. Okay, they are not the best rational approximation, but they are some rational approximation. So all of them, or most of them, let me say that because I don't know everything on that, look like what is written there, which is a sum of terms, CI, and you have in the denominator Laplace plus a pole. Okay. Specifically for when d when you have only one power, d to the s, these poles you can prove they're all positive, and this makes this very stable. If you look at the best approximation, okay, and many of the techniques like using time-dependent problem to do this, they also lead to positive poles. If you have negative pole, this could not be good approximation. Okay, so instead of having in the preconditioner here this fractional, you can definitely replace it by the rational approximation. Now, what is NP? Okay, this I just want to say this is very. If you want to approximate this, think about this as a function of x to the s plus beta x to the negative t. If you want to approximate this function by a rational function to the machine precision, the ones that I have tried, you usually need between 20 and 30 poles. If you want to use it for preconditioning, you can, I think, get away with 5 or 6 at least. Because then you don't need machine accuracy. Okay. All right. So that means that we have to know how to solve many Laplacians. 20 Laplacians when you apply the preconditioner once. Or, well, I want to say that, but maybe 4. Okay. And here is a typical 1D network. Okay. And I'll give you on the next slide. I have a movie here. How the mesh is built, but I'll show you the mesh. I think we can forget the movie. So on the left is the network, In the middle is the mesh built in a way that every tetrahedron contains 2 points from the 1D graph. Okay, this on the left is also a graph. It has vertices, so every tetrahedron in the center, that it has no more than 2 vertices. The mesh looks uniform because we have expanded a little bit the bounding box to contain the whole network. But if you cut it in the middle, you can see how adaptive it is. Okay, so and this kind of 3D 1D, one wants to solve on this type of mesh. And yesterday we had a wonderful talk by Anna on this. Okay, so I'm going to move on to talk about how one can use a posteriori. This is an application, okay? So I'm not going to go back to this 3D, 1D or anything like that. The idea here is not the idea, but the focus is how quickly we can solve a Laplace equation or Darcy equations, using algebraic multiplication. Okay. So one looks at this U equal to F, which we started with, and so there are out there adaptive linear solvers. Okay, none of them, in fact, uses the right-hand side. So if you think about adaptivity in finite element, the right-hand side is used all the time. Here, somehow nobody uses the right-hand side, and so we thought it's a good idea to actually try to bring this in. Okay. So the questions are there at least partially one can extend what is done in finite element, finite volume, finite difference to construct adaptive multi-level hierarchies of spaces. Okay. Usually adaptive finite element method, you have some mesh, you have your piecewise polynomial space, and then you construct a better approximation by refining the grid. Here we want to go backwards. Okay. So that means we're going to define some subspace and then try to judge the error. Of course, it's the same as what we had before because we don't know the solution. Okay. So I cited here several of the earlier and also later works on adaptive AMG or algebraic techniques that try to adapt to the operator. So they don't use right-hand side. Adaptive multi-level ILU, that is Durand Bank. We have alpha AMG, that's the classical AMG Duruy-Stuven and made adaptive, and also adaptive smoothed aggregation. If you have ever heard that, this is in Trilinos, for example, if you know this package, it uses smoothed aggregation. I don't know if it uses adaptive, but it does use smoothed aggregation. There is another bootstrap AMG, which is Buroki Brandt and James Brannick and Quarters. And Pasqua and Pasqua Dambra and Panayot Vasilevsky, they have this adaptive matching, which is one of the methods I actually like because I think it can work also for non-symmetric problems and things like that. Okay, so I will kind of show until the end how much, when should I stop? Okay, so I will talk about a bit about adaptive path covering and of a graph and how this helps us to construct Coarse space. Okay, so this is our graph, and we do matching, means we pair vertices together, and if 2 vertices are paired, they cannot be paired somewhere else. Okay, so here is 1 and 2 are paired, this and this, and if there is something isolated, like 7 was isolated, like the 7th floor here, you add it to something that has fewer vertices in the neighborhood. Okay, so now if you want to think about functions, think about piecewise linear function. And once we did the matching, the subspace corresponds to functions that have the same value on every edge. So that means the value at vertex 1 is equal to the value of vertex 2. It doesn't have to be equal to any of the rest. And the values of vertex 4 is equal to the value of vertex 6 and so on. Okay, so this looks like functions that are constant at some place. And this is when we restrict, so to say, the graph on this subspace, how the new graph looks like. Okay, every pair is connected to the guys that were connected before, so to say. Okay, so what we're gonna do is we're gonna do adaptively the hierarchy during the iterations. That means we can change the, if we see that we make a big error because of some aggregate, because of some matching, our matching is wrong, we're gonna switch. Okay. So we can do this by using the so-called maximum weighted path cover. That is, for a given graph, you try to collapse all the edges in paths such that the sum of the weights is maximum. Okay, and so if you have some approximation to the error, let's go back to what we are talking about. Then you can construct an auxiliary graph with weights 1 over the difference on edge of the error. Okay, so that means if two values are close in the error, this is going to be big. Okay, and when you do maximal path covering, thinking in a very simple way, this will recover the level sets of the error. That you can think it does that way. Okay. And so if I give an error, it really does that. And if I construct my piecewise constant space right here, based on such pairing, the error is 10 to the negative 10. That means if you have a smooth error, which is always trouble for multigrid, you can find the level sets and approximate the error with constant, piecewise constant, and then you're fine. Of course, you cannot do that because you don't know the level set, the error. I mean, otherwise, everything is solved. Okay, sometimes one needs to do tricks to take all the parts of distance 2 and put them together in order to have nice nice so-called aggregation. Okay. So here is the practical adaptive algorithm, which is as follows. So we run W cycle. So in algebraic multigrid, there is D cycle and W cycle. Think about W cycle is more expensive, but hopefully will bring you closer to your solution. Okay. So you take the difference between what you have now and what you have from the W cycle, and you say, okay, this is my error. And those are the level sets that I'm going to approximate. That's basically it. Now, this makes an expensive method, but as I said here, we don't solve Laplace on uniform grid. This is for some other things. Okay. So sometimes this pays off. And here are examples from sparse matrix collection that I have. You can see they have, those are matrices. Every matrix corresponds to a graph. And we have like 22 million and 100 million and so on. And some other ones from the Stanford data set. And so I'll say what each of these is. So one of the columns shows the convergence rate. If you see convergence rate of 0.99, this is not a multigrid. Okay, that's really bad. So if you run some standard coarsening, not following any matching, any error or whatever, you get 0.99. And same for the other grids. And you can take random F, do the W cycle, and so on. And I don't know why I don't have. Yeah, okay. So the question then was how one can actually make this more practical by not doing the double cycle iterations. Okay, and get the error. And what we use here is the so-called Prager-Singe identity for people who do a posteriori error estimates. Not only this is a result that is known. And okay, so Prager-Singe gives you, if V is approximation to U, this is your error estimate. L here is the Laplacian. And of course, this is also not very practical because you need to know the value of the Poincare constant, which you don't know. That's the minimum eigenvalue of the Laplacian. How can you know? Okay. So, and what our observation was that we can actually localize this by looking at the graphs spanning trees and cycle space. And then basically what this amounts to is, so this is in this paper, it's already out. What this amounts to is trying to compute approximately this tau. And it turns out a few iterations of Schwartz method will give you a very good estimate on the error on tau. I think I have experiments like that somewhere. So this corresponds to a Helmholtz decomposition. When I say the graph you do spanning tree and cycles, this is like Helmholtz decomposition. It's the same. Okay, so to find the solution on the spanning tree is very easy because the tree you can do LU decomposition without fill-in. Also, that is used here. And the difficulty is to solve the cycle space, but to solve the cycle space, you just use Schwartz method. That's enough. I mean, you don't want to resolve everything. You just need to know where the error is constant, right? Something like that. Okay, so here are more details about the how this Helmholtz decomposition is done. This is actually the slide. The Don Rose had this paper about the fill-in in when you solve tree, you don't have any fill-in. I think actually at some point Ilaria Perugia also wrote a paper for Maxwell based on some similar things. Okay, so let me go to numerical experiments. So we do Schwartz method, and one has to use some of the latest developments in this enumerating cycles and how to find them. Okay, so here is what we have. We look at this EFF is how effective our error estimator is. Okay, so we see that we have constants of 2 or 3. I mean that's most. And for some of the so-called real-world graphs, we get close to 1. I have to tell you that my experience shows that actually uniform grid is the hardest problem for those kind of things. I mean, if we didn't know how to solve uniform grid in a different way, we would have trouble. But okay, so this is the error, and this is how many Schwartz iterations are done in order to say where the error is a constant. And we aggregate along the level sets. And this is just with a smooth error and with the error estimator, you see that the aggregation is the same. I mean, okay, not the same, but very close. Okay, so let me go to the summary. So I just want to say operator preconditioning provides some paths for constructing error indicators, but also goes back the other way. Okay. So approximations, I know this AMG, I mean, one can give a talk only on how to do a posteriori error estimators in AMG and these Helmholtz decompositions. I wanted to put them together because they somehow show that one can cross a bridge going to a posteriori and then come back. We have this software that we developed, Cosmix, which is also Anna showed some examples, and we try to do these 3D, 1D problems as part of it, or Darcy stocks coupled through an interface, and so on. And here are two of the papers that we recently have submitted, and the software that we have used. And I think, thanks to Paula for inviting me, and I would like to acknowledge the support from US Norway Fulbright Foundation and from NSF. Thank you very much.
Thank you, Ludmil. This very interesting talk. So I ask if there are some questions or remarks also from home. Thank you.
Okay. I would have a question about the right preconditioning actually, and I was wondering about whether this let's say this framework can be sent to the right case where the risk operator is not there.
You mean the right preconditioning? Yeah, so you have A, B.
Exactly.
B is on this side, so I'm going to tell you. Okay. I can tell you which paper that.
Okay, because I was wondering whether there is no preconditioning of the right side. So,
I mean, I haven't looked at that, to be honest, but I know that which one? Let me see. This one here, and search for MA at Penn State. She graduated in 2016, but her thesis is available online, and there is, I think, all of them relating them to filter values and so on. Yeah, I can email Paolo that.
Thank you. It's just a matter of notation. So the graph fashion is called like this. The fashion of the differences that we.
Yeah.
I thought in order of construction of maybe are listed. The whole thing depends on the position of the node and the distance to the graph, but not on the actual nature that could be, for instance.
But it depends on the edge weight, because the edges can be weighted. And in fact, if you do Darcy with jump coefficients, the edges will have different weight. You know, if you look at your
geometric system, we show this fantastic examples of all the possible roles in the United States. In this case, when you just compare the physics, you go to the graph.
Yeah.
You have a way for how the influence atoms are connected to them.
I'm just going to say that you can put weight, which would mean, like, think about the cost if you're talking about the road network. What is the cost to go from A to B? And that could be your weight.
So there's a way to calculate them functionally.
Yes, yes. Yes, yes. I mean, graph theory is just notation, if you ask me. I mean, it's just some notation. Edges, vertices, and you don't have anything more. I mean, the rest of it you have to construct.
But what is so surprising is that all this theory is, as I understand, that the robust is to the actual topology. So you may have very short path and long path, and it's big weight and basically,
yeah, that
is fantastic. So
Big,
different to that.
because we account for the weights. I mean, if you say short, what do we mean by short? How do you measure short? I mean, maybe you have a lot of atoms. I don't know. I mean, it depends on how you define distance. Let me put it that way.
Any other questions? Gabriel?
You showed this block diagram in figure issue where the bottom right block you have this with a star there, right?
Yeah, okay, yeah.
Excuse me, what's any relation between this one and the optimal block diagram figure issue that was produced by Ward and Roll collaborating to make the eigenvalues plus the eigenvalues? I mean, it's related in your way to the Schur complement. Is it?
Yeah, but the way we look at this here is that, you know, if you look at this from PDE point of view, when you take a trace, you have some fractional space. And as I was mentioning, it basically depends what is the norm on H. Okay. And when you define it for your operator, it comes out to be, you know, it is equivalent to the Schur complement if this is equal to 1/2. What if it is not? And actually, there are examples. I'm not good in modeling this, but I think Kent and Dremer has some examples where S is 1/4 and T is 0.64 or something. 1/10. Then it's different than the Schur complement.
Any other questions? I have a question. So when you make the analogy of the two-level Schwarz method, where the fine level is the infinite dimensional, and then the fine elements, finite grid is the coarse. So if I didn't miss any point, you use so you assume that the discrete space is a subspace of the continuous one. So I was wondering whether you can handle also the case of non-nested spaces.
Yeah, I'm going to say something here that maybe recently there are better works on that. But for example, if you want to estimate non-conforming, you always go to the conforming. So at the end, you use the subspace that is conforming. If you want to do error estimator, at least that's the papers I have seen. So that means, you know, you can think about VH always being conforming, even though it could be subspace of your original.
But in the Schwarz framework, the non-nested cases can be handled. That's that's my point. So is there an analogy also with the a posteriori stuff?
To say, I'm going to say this, I actually tried to do the non-conforming in that way, but we haven't finished this, and I don't, I think it's possible. Let me put it that way.
Because this would also open a further question in the a posteriori setting, where you have to always pass somehow to the conforming setting with some tricks or.
Yeah, one has to look at non-conforming Schwarz for non-conforming, how it is on the infinite dimension space. What does that mean? Then probably you can do it.
Oh. Okay. Let's check from home. Is there a question on the phone?
This is just a decision. Is NP equal to 20 that you put on the rational approximation? Is it just for the heuristic or is there any reason?
That is heuristic. I don't have, I don't have a bound on that. I mean, there might be some theoretical bounds on the. Oh yeah. If you, I mean, I have looked at this numerically, and it is correct. Or it's stable. Actually, we have. I quoted one of the papers. It has all these investigations for different alpha and for different parameters, different S and T, how the number of poles. that you need to achieve machine precision changes. And I think this is all bounded. I'm not going to say back 20, sometimes it's 40. But I mean, it is bounded. On all cases we tried, and there might be some theoretical estimate from approximation theory that I don't know on the number.
One fractional power.
For one fractional. Oh, yeah. For this, no. Oh, yeah. That's e to the square root of n with a negative. So e to the negative square root of n times pi actually is a bound above n. 3 is below pi. Now I remember because I taught that some class.
That's really the issue. Is there any point in your, say, development where organization is trying to set a jointness of value?
No, but well, we use the spectral theorem, right? So we use the spectral theorem that we can replace d by x and then approximate x, get the rational function, and then replace x back with the operator. How legit this one is, I think is okay in many cases. For non-symmetric, I don't.
Okay, if there are no more questions or comments, we can move to the